So hi, and welcome to the next in my series of videos drawing on things that I usually cover in the last few weeks of my course at SFU. And in this video, this is going to be the second of our deep dives into the Big Bang. In the first slideshow in this series, we imagined running the cosmic expansion backwards in time and discovered that the universe would have been in a condition that we sometimes refer to as a fireball shortly after the Big Bang. So a very small, very hot, and very, very dense. And then from that logic, we ran the movie forward from that starting point and deduced that the universe should be filled with the leftover heat of the Big Bang, which we refer to as the cosmic microwave background. Microwave because the wavelengths have been shifted from very short wavelength, high energy radiation in the early universe to microwave wavelengths today. In this video, what I'm going to do is introduce the first of several gorgeous animations that really help to illustrate some of the most mind-bending concepts in cosmology. These animations were created by a scientific collaboration known as WMAP. WMAP standing for the Wilkinson Microwave Anisotropy Probe. Like, what is all this? And so here's a picture of this spacecraft, which operated about 1.5 million kilometers away from the Earth in an orbit that kind of trails the Earth between 2001 and 2010. And so this was really a revolutionary set of measurements that helped to establish some very, very cool and surprising features of the universe. And so we're going to look at that by playing this first video, and again, one of several. So if you're looking for this, look up WMAP concept animations, and you'll find like a whole list, including this one and several others that I'm going to get to, not in this slideshow, but in the next one, the one after that. Okay, so as I play this animation, I want you to pay particular attention to two key features near the end. One is the microwave radiation temperature is shown to be almost perfectly uniform everywhere on the sky. And two, at the end of the movie, they'll turn up the contrast in the map of the radiation that they're going to show us, and that will reveal minute variations or anisotropies in the temperature from place to place on the sky. So there's that word anisotropy, and it just means it's slightly different in different directions. So in this first installment of the animation, we're going to follow it to the point where it makes this first observation. Now, one thing about the WMAP animations, they're very rich and full of subtle information, but there's no narration. So I get to make up the narration as we go. And so again, this satellite trailed the Earth in our orbit around the Sun and looked out into space to receive microwave radiation coming to us from all directions, coming to us from the Big Bang in every direction in the past. So in this animation, they're going to fly into the plane of the Milky Way galaxy. That's our galaxy. And then they're going to find the Earth and the Sun, and they're going to construct a celestial sphere surrounding the Earth. And then they're going to unpeel that sphere the way one often does with maps of the Earth's surface. So now they're going to show us the view of the sky. Remember, the whole sky has been unpeeled and put down on a flat piece of paper. And so this is the Milky Way here in the middle, and that's the rest of the sky. And so now they're going to scan through our view of the Milky Way and the sky through different wavelengths, starting here in the visible. And since we want to look at the sky in microwave, we're going to scan over to longer wavelengths. And so there's near infrared, far infrared. That's another kind of infrared. And here's microwave. So now we've reached this first observation. So this is meant to represent the temperature in different parts of the sky. And we still need to understand how they measure the temperature, but so this shows an area all around the Milky Way galaxy where Okay, the Milky Way, we're not going to be concerned with the Milky Way so much as the rest of the sky. And this shows that the temperature seems to be almost identical at every point in the sky. So a natural question at this point arises, what is this statement trying to tell us? Why should the radiation be characterized in this way? Well, we already really anticipated this from our previous video of running the cosmic expansion back in time and discovering that the universe must have been small, hot, and dense, and then running the movie forwards and being filled with the leftover heat of the Big Bang. And so that's what this map is telling us, that yes, there is a radiation that comes from every point on the sky. It's not associated with anything on the sky, but there's the Milky Way galaxy. This has got nothing to do with our galaxy, really nothing to do with anything else but the universe itself. And one might have guessed that when the universe was created, that every point in that small, hot, and dense region would have been almost the same. And therefore we get almost exactly the same temperature in terms of the radiation coming to us from the universe itself, as seen in different directions. I just want to clear up one potential source of confusion in interpreting a map like this. It's natural to think of this shading as representing the intensity of the radiation that's coming to us from different directions, but that's not really the point here. What we want to know is the temperature. So how are we supposed to measure the temperature of the sky, no less? Well, this brings us back to a topic that also seems like it came from a previous lifetime, many weeks ago in our course, and that's when we introduced the black body spectrum. And so just to remind you a little bit about that discussion, a black body is defined as an object that absorbs all radiation that lands on it and reflects none. And so these curtains are not perfect black bodies because you can see there is some reflection, but they're pretty close. So then one might say, well, why should there be a spectrum coming from a black body, something which absorbs all radiation? Well, even if it started off stone cold, it would get heated up by the radiation, and then in turn those atoms and molecules inside the matter would radiate. And so a black body is not necessarily black. In fact, the sun is a black body, as strange as that might seem. So, any stray bit of radiation that might run into the sun is almost certainly going to get absorbed by this giant ball of gas, but it's most certainly not black because the atoms, molecules, particles inside the sun are at very, very high temperatures and thus they will radiate. So the term black body can be a little bit misleading because a black body appears black to our eyes only if it is at very, very low temperatures, although it's still radiating, let's say, infrared. And so one more feature about black bodies that we talked about way back when is that they are characterized by a very sort of what you might call a universal spectrum. We say the spectrum is universal because it depends only on the temperature, not on what the object is made of. It doesn't matter what's bouncing around inside there of some particular black body. The spectrum will be the same for any two black bodies with the same temperature, though a bigger object would be brighter overall. And so you might remember some features of black body radiation. In particular, all colors are present, we like to say, although some colors dominate. And the dominant color is determined by the temperature. And the cooler the object, the more the dominant color will shift to the red end of the spectrum, as well as for a cooler object, the overall intensity will go down. So in the case of the universe itself, we're not interested in colors per se, but we're still talking about black body radiation. Why should the universe be characterized as a black body? Isn't that kind of odd? Well, the thing is, imagine sending out a little bit of radiation into the universe. Well, it's not going to get reflected. It's going to disappear and never come back, at least not the original radiation. And so that's what characterizes a black body. And so a strange way of characterizing our presence inside of the universe is that it's like we're inside a very weak microwave oven. It's microwaves, although the strength of the radiation is not appreciable. If you were in space, you wouldn't even notice this stuff hitting your body. So a crazy concept, but nonetheless, this follows from very general principles. And so when this prediction was made long before measurements of the cosmic radiation were first done, the fact that the universe was expected to be a black body and probably not very hot, since it's been a long time after the Big Bang, a definitive prediction was that the radiation coming to us from the sky should follow a black body spectrum. And yes, the measured CMB does perfectly follow a black body curve. Now this result comes from WMAP. This is not the first mission to measure the spectrum in this way. We'll get to who did that first shortly. But the point here is that the intensity of the radiation coming to us from the sky as a function of wavelength does follow a black body curve. And today the measurement has been done of this curve so precisely that one knows the temperature of the universe itself to astonishing precision. The temperature of space, the radiation traveling to us that today from the Big Bang, has a temperature of 2.725 plus or minus 0.001 degrees Kelvin, 1 part in 1,000. That's an astonishing result. And so to do that, they have to measure the radiation as a function of wavelength. And to know that the temperature is almost perfectly uniform everywhere on the sky means that they have to measure the radiation as a function of wavelength in essentially every direction. So now we get to the second and final part of this first video, where the purpose is going to be to turn up the contrast on their map of the temperature across the sky. And that's going to show that, in fact, it's not perfectly uniform. There are minute variations in the temperature from place to place on the sky. That is to say, there are anisotropies in the temperature distribution. And so before we look at the video, you might ask, well, why should there be anisotropies and what's the big deal? Well, it is quite a big deal because some anisotropies in the universe itself, some differences from place to place, had to be present, because if the universe started off perfectly uniform everywhere, then there's no way that the universe could have evolved into structures like galaxies, stars, and us. There had to be places where, for example, there was a little more mass, or a little less, a little hotter, or a little cooler, and those regions would then be the seeds for the formation of structures later on. And that's a story that we'll tell in the third video in this series. Okay, so let's watch. So I'm starting again from the beginning. And so as before, we're going to, they take us into the plane of the Milky Way galaxy where our solar system is formed. And they're going to construct a celestial sphere around the Earth. And then they're going to unpeel the sphere and lay it down on a flat piece of paper like you do with maps of the Earth's surface. And now they scan from visible out to microwave, where we finally find that temperature that comes from everywhere. And now they turn up the contrast. That is to say, they look for small variations in the temperature from place to place. The temperature overall has been measured to 1 part in 1,000. The variations from place to place are about 10 times smaller than that. And so these are very small variations from place to place. And so here the Milky Way shows up in a big way because it has its own microwave radiation. And so the temperature here is different from the temperature of the radiation associated with the universe itself. And so when astronomers present a map like this, they tend to try to filter out the Milky Way and show you what they expect to be there left over from just the Big Bang itself. And so this map of temperature variations from place to place, tracing back to the earliest moments after the Big Bang, this is sometimes referred to as a baby picture of the cosmos. And so the baby picture doesn't go back all the way to the very, very beginning. For reasons that we'll get to in the third and final video in this series, the radiation dates to about 400,000 years after the Big Bang, which is not much considering that the universe overall is about 14 billion years old. But the reason why this radiation short story dates to this time and has not changed since then is that after this, after 400,000 years, the radiation had too little energy to interact with matter with stuff that was in the universe. And so after it was released from its early conditions, it traveled to us unaffected by the presence basically of anything else. So this radiation that we detect here on the Earth today at 14 billion years after the Big Bang, this is a relic of the Big Bang hot fireball. And that relic has not changed for almost the entire history of the universe for this reason. And again, I'll discuss this in some more detail a little bit later. And so just to give you a better sense of the history, since this is such an important result and it's so central to our understanding of the origin of the universe, I want to give you a sense of how these measurements came to be, who did what, when. And just before launching into that, again, I'll remind you of the idea of the anisotropies. Why are they so important? Well, here's the structure we see today in this gorgeous image from the Hubble Ultra Deep Field. And so this map of the baby universe had to, over time, turn into the structures that we see today. And in particular, if the map had been totally uniform, then this wouldn't be here. And so history, the first people who actually detected the radiation from space, Penzias and Wilson, they did that essentially by accident. It's a very interesting story, and I encourage you to look it up. But despite the fact that they found it by accident, this is an astonishingly important discovery because there was the leftover heat. So they got the Nobel Prize in 1978. Now, they didn't measure the black-body curve, nor did they find the anisotropies. They just found heat, radiation, microwaves coming to us from every direction. The measurements that established the black-body curve and at the same time found the anisotropies, which had to be there, that was an earth-shattering scientific mission known as COBE, the Cosmic Background Explorer.
Just what did you mean by that crack about the Earth being gone?
Oh, I'm going to blow it up. It obstructs my view of Venus.
It does? That's a shame.
Where's the kaboom? There was supposed to be an earth-shattering kaboom.
That was an earth-shattering scientific mission known as COBE, the Cosmic Background Explorer, that I believe is in orbit around the Earth. And John Mather and George Smoot, co-leaders of this enterprise, they received the Nobel Prize in 2006. And if you're a fan of the Big Bang Theory, George Smoot has a guest appearance in one episode where Sheldon is hoping to get a paper with this guy. Okay, so that's the map that COBE first found of the anisotropies. And so, it's a little hotter here and a little cooler there. This is what you might think of comparison with that to be a crude map. I mean, no map was present before COBE. And so as soon as this result was obtained, and yes, the anisotropies are in fact there, as had been predicted for decades before they discovered it in the early 1990s, well, then the hunt was on then to make these measurements with more precision. And that came later, and that was the WMAP probe, and that's the map that I showed you. So this was a huge advance, not even 10 years after COBE. They go from sort of a crude overall sense that there are variations to this much, much finer level of detail. And in the third video, I'll tell you why it's so important to have the detail, not just the existence of the anisotropies. And finally, the last mission to do this was a satellite launched by the Europeans called Planck, and they made yet another improvement over WMAP. This is about a factor of 3 times finer in detail than that. Okay, so I hope that wasn't a complete overload. And so at this point, I'm going to sort of play this game that I did in my previous video and give you a breakout question of the style that I would have had if we were actually together in class. So here's the setup. The cosmic microwave background, the CMB, the radiation from the Big Bang, the leftover heat has been mapped in great detail. And the question is, what does that map look like? And here are 5 choices. The map is generally uniform all over the sky. If you look very closely, there are slight fluctuations from place to place. It is seen even where space is empty. And then what I like to call my two weasel choices, which sometimes turn out to be right. All of the above, both A and B. So I'm not telling you what it is. You should pause the video now and take some time to think about it, and then I'll come back and give you my answer. Okay, so like I like to do in class, I call time. And here comes my answer. What did you pick? My answer is all of the above. And that basically encodes these two graphics, this crude one that I made and this fabulously precise measurement of the anisotropies from Planck. And so, yes, it is generally uniform all over the sky because the Big Bang, we see the Big Bang in all directions. And the Big Bang was the conditions in the early universe were mostly uniform. But if you look very closely, there are slight fluctuations, anisotropies from place to place in the temperature. So they had to measure the full wavelength spectrum, say, in that direction, and then measure the full wavelength spectrum in that direction. Actually, they compared these sort of different directions simultaneously. And so you see slightly different temperatures coming at you from different directions. So those are the fluctuations. And then perhaps the most surprising statement here, it is seen even where space is empty. Well, that's because this radiation has nothing to do with our galaxy or with any galaxy or any entity that is present in the universe. It is from the Big Bang. It is radiation of the universe itself. Okay, so time for me to say goodbye until we meet again in my next video. In the meantime, with all this craziness going on all around us, please stay safe and healthy. Bye.